You can find your own method, but this is the way I teach it. All right, so we have this integral. Find the antiderivative of x, e to the x, dx. All right, so I look at that. The first thing I do is make sure I don't know how to do it with some other method first. And then I say, okay, integration by parts, let me give it a shot. So I need to choose a u and a v, right? I need to figure out what u and v are. So I'm going to go back to this form. Actually, I should write it this way. I need to write u and then dv, right? Those are the two things I need to identify over here. So the way I do it, again, is this. I make a table. I put u here, and I put dv here. That's just the way I do it, okay? If you don't like it, you don't have to follow it. I'm going to choose what those are right now. So what did we want to use for the u? The x. So this is going to be x. And the dv would then have to be the other stuff, right? E to the x. And then I'm going to bring the dx with it. E to the x dx. That's what I've chosen, right? And I'm keeping in mind, the reason I chose this to be my u is because in the new integral, it's the derivative of that, and it's going to turn into a 1. All right, so now I'm going to complete this table. And the way this table works is that if you go down on the table, you're taking a derivative. And if you go up on the table, you're taking an antiderivative. All right, so I'm going to differentiate down here. What's the derivative of u? Well, du is this derivative, which is 1 dx. Make sure you put the dx there. And then here we do antiderivative, right? From dv we go up. That'll create v, won't it? And that'll be e to the x. Now I know you want to put a plus c there, but don't worry, we're going to put a plus c at the very end of the problem. So don't worry about a plus c here. And then once I have the table, I just go to the answer. This will be equal to ultraviolet. Ultraviolet are these two multiplied, aren't they? So x times e to the x minus the integral, and now voodoo, right? Voodoo is always this diagonal from here to here. So that times this. And then we already know what that becomes, right? Because the antiderivative e to the x was e to the x. So we get x e to the x minus e to the x plus c. Done. Questions, comments, concerns, complaints, gripes, anything? Yes?
So we're just going to put the u equals x on top, the top left, and
I'm always going to do it that way.
okay. So
Every time I set up an integration by parts problem, I'm going to put a u here, I'm going to put dv here. I'm going to figure out what I want to choose for those two. I have that control. This and this I choose. And then once I choose them, I'm going to differentiate down here and integrate up here. Yes?
Does this only work for those with two equations?
Nope. We'll do some, I'm going to get to some that, yeah, you can, just not quite yet. We may get to it today. All right, how about that one? Let's do that one. This is an example of a basic integration by parts problem. It's very similar to the one we just did. So it's x sine of 10x dx. Quick time out here. So chapter 6, yeah, section 1, integration by parts. The next section is called trig integrals, all right? Then we're going to do trigonometric substitution, then we're going to do partial fraction decomposition. When you start putting all this together, what makes the next test, not the one you're going to take next class, right? You'll have a test next period. Not that test, the one after that test. What makes it so hard is that when I give you an integral, you don't know what to use, all right? So you got all these different things Right now we really only have like two things. We have basic U substitution and then this. But we're just, if I give you this on the test, it's going to be just a basic problem. It's not going to be an advanced problem. All right, so it's harder later because there's no indication, there's no guidance. You know this is integration by parts. You know it is because I'm doing integration by parts right now, right? So that becomes part of the big challenge later, is identification of the problem and what to do with it. And that just comes with practice. Practice, practice, practice. And then you see it and you're like, I know I've done something like that and then I did this, all right? But you have to get that repetition, problem recognition. All right, so let's do this. This is integration by parts. If the x wasn't here, this would not be integration by parts, right? This would be a basic problem, but the x is there, so that's an issue. All right, so I'm going to try integration by parts. I'm going to create my table, and I'm going to choose a u, and I'm going to choose a dv. So what would you choose for u? X. Why? In the new integral, it's going to be a 1, right? So let's go for it. X, and then that forces this to be what? Everything that's there, right? Sine 10x dx, the whole thing. Now complete the table. So we take the derivative. What's derivative of x? 1 dx. What's the antiderivative of sine of 10x? Negative 1/10 cosine 10x, right? Didn't we do that before I started this today? Like I did that over here and we came up with a formula and you all said you felt comfortable? Negative 1/10 cosine 10x. Again, no plus c here. We're going to get a plus c at the very end. Any questions? All right, that's it. Right now, before I even continue, the new integral has what in it? Voodoo, right? Voodoo is this and this multiplied. I'm looking at it right now. Am I going to be okay with negative 1/10 cosine 10x times 1? Is that going to be something I feel like doing? Yes. So I'm going to continue. So this becomes ultraviolet. That's these two multiplied, right? These two multiplied. Watch the way I do that. I'm going to put the constant out front, then the x, then the cosine 10x. Right? So because this was an x, I didn't want to put it in front of the negative 1/10. So I just put it right behind the negative 1/10. Then minus, and then I have an integral, right? Yeah, when I do this, this times this, that negative 1/10 right there is a constant, right? And it can come out of the integral. So I'm going to take it out right now. Is that too much? Or do you want me to leave it in right now, or can I take it out? What do you want me to do? Take it out? If I take it out, what's going to be in front of that integral? Plus 1/10. And now I still have the cosine 10x, don't I? And I had the 1 dx, so I'm just going to put dx back here. Any questions on why that became a plus 1/10? You're all right? All right, now we just have to take the antiderivative of this. Do you know the antiderivative of that? I hope you do. Plus 1/10. Okay, here it goes. Here's the antiderivative. I've moved all the way up to here. Now I need the antiderivative. What's the antiderivative? 1/10 sine 10x, right? 1/10 sine 10x. And I already had a 1/10 out there, didn't I? Now I say plus c. So final answer, negative 1/10 x cosine of 10x plus 1/100th sine of 10x plus c. I'm just curious. I'm going to Wolfram alpha to do this problem? X times sine of 10x dx. Shit, what happened? There we go. Okay, so it didn't do any crazy. Sometimes it does like crazy trig identities, and your answer here looks completely different than the answer there. But that's the right answer. That's the same answer. So, did I do what? What?
Negative 10x instead of 1/10.
Negative 10x. Yeah, no, distribute. If you look at the 1 over 100 out front, distribute it through. Do you see if you distribute it through, the first thing you get is 1 over 100 sine of 10x, and then when you distribute it the second time, the 10 and the 100 reduced to be 110? Question back there? Was that the same thing? Yeah, it looks different. It's the same thing. But sometimes they'll use some weird-ass identities, and like the answer looks nothing like this, and that's how I can always find students. It's not so much here, but like my online students that turn in, answers, and it's like, no, that is a computer answer. Like you're never using those identities ever, So I just wanted to see if it would do it. Questions? All right, so we had a question. Does it ever come up that you don't have two things, right? Like, who said that? Who asked that? Okay. So how about this? This is a classic problem. Natural log x dx. Let's put a star next to this. When we're done with this problem, I am going to allow you to hand write this onto your formula sheets. You can add this to your formula sheets by hand, okay, when we're done with it. So we all know what the derivative of natural log is, right? But what's the antiderivative of natural log? Don't know, right? Don't know. And there's nothing that we know up to this point that's going to allow us to figure that out. But now we have this super powerful integration by parts. Now look, integration by parts is not like the magic pill. Not every integral can be solved with this. It's just a new tool, but it's a heavy, heavy hammer, okay? We can do a lot with it. So let's just try it, okay? We have to take a shot. So if you're going to do this, u in dv, you've got to fill these pieces in, but you only have one thing here, right? Like only one function? Or do you? Well, you could let this natural log of x be u, couldn't you? But that would force dv to be what? 1 dx. Right? So you're looking at this as natural log of x times 1 dx. Think about the new integral. Think about the new integral. Derivative of this? 1 over x dx, right? What's the antiderivative of 1? X. Look at voodoo. Look at voodoo. Don't those x's cancel and become a 1? Can you find the antiderivative of 1? I think so. Right? This is going to be nice. Yeah, so this is going to become, let's see, ultraviolet. What's ultraviolet for us? Natural log of x times x. I'm going to rewrite it the other way. I'm going to write x times natural log x. Why do I write that instead of this? Why do I write that instead of this? That's right. Someone could get confused and think what I mean here is natural log of like x squared. If I wanted to write it this way, to be real precise, I should put that x in parentheses if I'm going to be careful. All right, minus integral. Whenever I do my ultraviolet minus voodoo, when I do my integral here, I always leave like a space here just in case I'm going to pull a constant out. In this problem, I'm not going to pull a constant because it's just x times 1 over x. Right? Do I need to? Well, I'll write it. X times 1 over x dx. But that's just x natural log x minus the integral of 1 dx, and the antiderivative of 1 is x. So that's your answer. X natural log x minus x plus c. That's pretty awesome, huh? Let's check our answer. If I take derivative of this, I better get what? Natural log x. Okay, let's see. If I did that, I have a product rule here, right, don't I? Okay, so let's do that real quick. I'm going to derivative, I get 1 times natural log x plus derivative of natural log of x, which is 1 over x, times the first function, which is x. Done with that, minus derivative of x, which is 1. This over this is 1, minus 1. Those cancel, and all you're left with is that. It works. How do y'all feel? So, is this okay so far? Let's try another one.
Do we ever have to worry about a C when going from DV to B?
When you go from here to here, you never have to worry about a C because it will be taken care of when you get to here. I know that's a little weird, but you don't have to worry about it. This takes care of it.
So we could write that on our formula sheet.
This you can write on the formula sheet. Well, what I would write on your formula sheet is this. Antiderivative natural log x dx equals x ln x minus x plus c. That's what I would put. Yes?
So is that, like, if that was ever on a test to take the antiderivative?
Of natural log of x, you could just go to this. You don't have to show it. Yeah. Ready?
Would we need the absolute value of the natural log?
No. No. How about that one? You can't use the formula that we just created, right? You can't use that formula because the formula only works if you just have natural log, right? What is your gut telling you? Let u be x, right? Because in the new integral you have 1, right? Okay, let's see what happens. So we're going to let u be x, but that forces you to make dv what? ln x dx, right? So I agree with you. If we do this, du would be 1 dx, which makes me real happy, right? This makes me real happy. But what am I not happy about? This to here. Now, to get from here to here, you need the formula, don't you? The one we just created. So we have it, don't we? It's x ln x minus x, right? So think about voodoo. Do you really want to do voodoo? Do you really like this new integral? Imagine if we had to integrate this. Not very nice, right? Does everyone see that? That this isn't, even though, yes, the x here becomes a 1 and we're like, yay, the dv becomes this and that's crap I don't feel like messing with, right? Now I might have to, but I'm gonna just look at maybe another approach. Maybe I should let the u be the natural log and let the dv be the x. And then that goes against what I basically just told you to be looking for, right? I said, look, the x derivative becomes 1, yay, right? We're happy. This goes against that completely because here I'm letting the dv be the x and we know it's going to get more complicated, right? When we go up from here, we're going to get a 1/2 x squared. Normally that would be something we want to avoid, but here it's going to work. Why? Because what's the derivative of this? 1 over x dx, right? And then when I do the antiderivative up here, 1/2 x squared, now my voodoo is not that bad, right? One of those x's is going to cancel. I'd rather do this than this, wouldn't you? So we're going down this road. Ultraviolet comes first, right? 1/2 x squared natural log x minus integral. I left some space here to pull out a constant in case I need to. And now I need the voodoo, right? These two multiply together right there. Can I pull a constant? Half, right? Pull that half. Doesn't change the negative though, right? This is still minus, but the half came out. What's in the integral? Just x, right? Because you're doing 1 over x times x squared, one of the x's cancel. So you get x dx, and I'm like really happy about that, right? I'm really happy about that. Questions, comments? One half x squared natural log x minus 1/2. Okay, antiderivative time. I've done all of this, right? Antiderivative of that is 1/2 x squared, right? So I have another 1/2 in front, x squared, and then plus c. Am I going too fast, or y'all keeping up with this? How do you think you get good and comfortable with this? Practice. Practice, practice, practice. The worst student is the one that watches me do this and is like, yeah, I got it. I can do that. No problem. Never touches the piece of paper, comes in here and takes a test and fails and wonders why, right? You've got to get your hands dirty here, right? Watching me do it is one thing. You doing it is something else. Yes?
You said it's important to put the absolute value of x. This, do we need to, when it comes to the natural log?
That was for the antiderivative of 1 over x. If you do the antiderivative of 1 over x dx, this is natural log of the absolute value of x plus c. The reason why we have to have the absolute value here, all right, the reason we have to have absolute value is because this function, 1 over x, is defined for both positives and negatives. Do you agree? You can plug positives and negatives into this. But the natural log, you can only plug in positives. So we put the absolute value around it so that you can increase the domain to include things that are allowed to be plugged into here. Yeah? But if you're doing the antiderivative of natural log of x, right, then whatever our answer is over here, we don't need absolute value because the domain of this is already restricted to only positive numbers. So that's going to restrict this domain as well. Does that help? Okay.
So if we put the absolute value, is it wrong?
It wouldn't be right. No, it wouldn't be right. Because, well, no, because then you could plug negatives in here, but you can't over there. Right? Like if you put an absolute value here, then you could theoretically put -2 in here, but then -2 is not allowed over here. Right? All right. So I've given you a good mixture so far. I've shown you where, you let the u be x because it gets nicer. I've shown you an example where you don't let the u be the x because that gets worse. Shown you one where there was only one function, natural log of x by itself. How about something like this? X cubed sine of pi x dx. How are we doing on time? 30 minutes? What's your gut telling you here? Let u be the what? Let u be x cubed? If I do that, that forces me to let the other part dv be sine pi x dx. Let's try and look down the road. Where's this headed, right? What's this new integral going to look like? Well, the derivative here is going to be what? 3x squared. And here is going to become a what? Some constant with cosine, right? So I've got an x squared term here. Yes, like 3x squared. But forget the constants. I can always pull those out. This is going to be x squared, right? And this is going to be a cosine function. And that's going to be my new integral. Do I feel like doing x squared with cosine? Probably not, right? But hold on, let's try it the other way. What would happen if I did this? What if I did the sine pi x here, and I did the x cubed here? Then if I go down here, I'm going to have a what? A cosine, right? And if I go up here, I'm going to get x to the fourth now, right? 1/4 x to the fourth. But do y'all see I'm going to have x to the fourth here in a, let me write it. I'm just kind of like, I'm putting on the board what's actually in my head, all right? What I'm doing in my head. This is a cosine. This is an x to the fourth. I don't know if I want to integrate that. Versus this is going to be an x squared. This is going to be a cosine, right? Do I want, which of those looks better? They both suck, right? They both suck, but look, this is x squared, that's x to the fourth. So what I've done by doing the integration by parts is I've chipped that power down from an x cubed to an x squared, right? I wonder, could I do integration by parts again? See, we're going to get a new integral, aren't we? That's going to have an x squared and a cosine. Could I do integration by parts on that one and chip the x squared down to an x? Yeah? And then do it again. Like 3 integration by parts. Yes? Oh, you mean like a plus each time? Let's do it and you'll see we don't. We just need a plus c at the end of everything. All right, so I don't want this. I don't want this because the x to the fourth power, all right? So I'm going to go to this one. All right, so here, let's go through the actual work. du is 3x squared dx. Please don't forget to put the dx here when you take this derivative. And then v here, now be very careful with all these constants. What is that? Negative 1 over pi cosine of pi x. No. Yeah, that's another shortcut thing. I like it. I don't not like it. This is the way I've always done it. Yeah. Okay, so this becomes ultraviolet, right? It's these two multiplied together. How would you write that? Negative 1 over pi x cubed. Is that all right if I do it that way? Like negative 1 over pi is a constant, then x cubed, then cosine pi x. That's ultraviolet, right? Ultraviolet minus a big space here. Now I'm going to do voodoo now, right? The diagonal. Let's look at the constants. That and that, right? A 3 and a negative 1 over pi are the constants with the voodoo. Let's pull that negative 3 times 1 over pi out. What's gonna happen here? What's this turn into? A plus, right? A plus, and then what? 3 over pi. Questions there? Right? I'm doing the minus that was here, then I pulled out a 3, and then I pulled out a negative 1 over pi. And then I put them all together and just got 3 over pi, positive. What's still in the integral? X squared cosine pi x dx. All right. I don't know what that is. It's not something simple. So what I'm going to do is everything after the 3 pi, I'm going to put in this purple bracket. I'm going to treat that like a brand new problem, and I'm going to go over here and I'm going to figure out what it is. And when I'm done, I'm going to come stick that answer back here. Understand? Let's start it right here. No, I'll leave myself space to put it in there. So this is my new problem. Integral x squared cosine pi x, right? I'm going to start a new integration by parts here. Right? U is going to be what? X squared. dv is going to be cosine pi x dx, right? This sucks, huh? You're going to have to do this more than once. You're going to, after you're done with this, you're going to have to do it again, aren't you?
Yeah.
Yes.
When we're doing it in like this, would we be able to, could we try like switching them? Or no?
What do you mean? Oh, if you switch them now, like if you change the order now, it'll take you back to where you came from. So you'll basically undo what you just did. So don't do that. Good question, though. The question was, in the new integration by parts, should maybe we let the cosine pi x be the u and let the x squared be the dv? Should we do that instead? Like switch them up, maybe it'll make it faster or something. Turns out it'll take you backwards because the x squared here would go back to an x cubed and the cosine here would go to a sine, so your new integral would be x cubed in sine, which is exactly what you started with. So it won't help you at all. But see, we're just chipping away at this, right? This is now 2x, right? dx when we take derivative. And then v here is, what is v? 1 over pi. Not negative though, right? Just 1 over pi sine pi x. So this becomes ultraviolet minus voodoo, right? So we have to do it again. So ultraviolet is 1 over pi x squared sine of pi x minus a space. Let's see. We have a 2 here and a 1 over pi here. I'm going to pull those out of the integral. Right, this 2 and this 1 over pi is going to come out. So this will become 2 over pi. And what's in the integral? X sine pi x. Hey, did we do this problem earlier? Just look in your notes real quick. I thought we did. Did we not do that?
We did x sine of 10x.
Sine 10x? Shit. Okay. All right. Then we just keep going, all right? So technically, right, technically here's where we are. Let's go ahead and just write where we are. Look, don't worry about how much paper you're using, all right? These problems, there's going to be problems where we're going to use the entire page, all right? Front and back possibly. There's some problems you're going to have to turn your page sideways because the line's so long, all right? So just get used to the idea of a lot of work.